Okay, welcome to the first lecture of this semester's General Physics and Exercise 2. So before we begin Chapter 21, let's make a brief overview of what we are going to study in this long course. The physics that we will study in this semester can be summarized in two words. One is electromagnetism, and the other is quantum physics. The word electromagnetism is a combination of electricity and magnetism. The electricity will be studied between chapter 21 and 27, and magnetism will be studied in chapter 28 and also 29. And we will then see that these two phenomena, electricity and magnetism, are not independent from each other, but they are closely related to each other. So the electromagnetism is a study of these two phenomena at the same time. And then we will see what happens when we make a wave out of these two properties. And this short chapter 33 is very important because these electromagnetic waves are in fact light that we encounter every day. And then we will study a little bit more detail of wave phenomena, which we already studied in the spring semester. Please remember that we studied waves in the spring semester, especially in terms of sound waves. But here we will study waves in terms of light or electromagnetic waves, and this will eventually lead us to the study of quantum physics, which is the physics of a very small scale, such as electrons or atoms. So this is the overview of our study in this semester, and it will be a very good idea to keep in mind where we are going. Okay, let's begin chapter 21, and then the title is Electric Charge. So in this lecture, we will first introduce a property of matter known as electric charge, or simply charge. And then we will learn where these electric charges of matter come from. And then we will eventually discuss the following properties of electric charges, such as types of electric charges, forces between two electric charges or more, and quantization of charges, and conservation of charges. And in doing so, the force between electric charges is the reason how we know that there are charges in the first place. So basically what it means is that we cannot see charges, and the only way we can know that there are charges is by observing the forces. And because it's involving forces, the Newton's force laws that you have learned in the spring semester will come back in this semester too. So if you had a good score in the first semester, then probably you will do fine in this semester too. Before we begin real lecture, let's try some simulated experiments. These physics simulations are provided by University of Colorado PHET Interactive Simulations program, and it can be found on the web page which is provided in the link. And I will try to use these simulated experiments as many times as possible throughout the semester. Okay, this particular simulation was designed to give you an idea about the force between electric charges. Now here we have a balloon and there is a sweater. Right now nothing's going on between the sweater and the balloon, but if you take the balloon and rub it against the sweater, then you will see that this balloon will get attracted to the sweater. Let's see it again. Now this time you take it a little bit further away and let it go. It still gets attracted to the sweater, which suggests that there is a force, attractive force between the sweater and the balloon. So what happened when you rub the balloon against the sweater? Now this phenomena can be explained based on the idea about electric charges. In fact, we now know that there are two different types of electric charges, and then we call one to be positive and the other to be negative. And originally, any matter will include the same number of electric charges between positive and negative. So therefore, it will be as good as having no electrical charges. But when you take the balloon and rub it against the sweater, you see that the negative charges are moving from the sweater to the balloon and effectively making the balloon negatively charged and then making the sweater positively charged. As a result, there will be an attractive force between these two objects. And then now let's try something a little bit more interesting. If you now take the balloon very close to the wall, you will see that some of the charges inside the wall get shifted, which means that now the negative charge on the balloon applies a repulsive force against the charges, negative charges inside the wall. And as a result, now it gets stuck again. Okay, we have just seen that electric charges are responsible for the forces in the simulated experiment. Then what exactly are electric charges? According to the definition in the wikipedia.com, electric charges are defined to be fundamental conserved property of some subatomic particles, which determines their electromagnetic interaction. So you can see that the definition in the wikipedia.com is not very easy to understand what it means. But basically what it means is that it comes from subatomic particles, and subatomic means something smaller than atoms. So basically what it means is that charges are something smaller than atoms. And it also determines what it means is that it determines the atoms' electromagnetic interactions. So, and what it basically means is that there is an interaction or forces between electric charges. And because electric charges exist inside atoms, this is the reason why atoms and matter do not break apart but hold together. Essentially, you are living because there are electric charges and keeps your shape as you are. And what we already know about electric charges, let's try to summarize. When charged, certain pairs of materials repel each other while others attract each other. This is just what we have seen in the previous simulated experiment, and it can also be seen in the pictures here. Here, the little girl's hair is attracted or pulled up by the balloon, which means that these two matters, the balloon and human hair, can attract each other. And there's another example shown here that this plastic comb is attracting the pieces of papers. And in certain cases, they can repel each other, just like the children's, just like this little child's hair. Here, nothing is pulling his hair up, but it is the many strings of hairs are actually repelling each other. That is why they look like this. And you see that what is actually happening is that the charges that repel each other are of the same kind, and those attract are of the opposite kind. And we typically call these two kinds to be, one is positive and the other is negative. And in fact, the sign assignment is arbitrary, and it doesn't really matter if you call the positive to be negative and negative to be positive. It doesn't really matter. But because of the historical reason, we assign some matter to be positive and some matter to be negative. And when these two types, positive and negative, combine with each other, they typically generate a spark and disappear, like we typically see in the case of lightning. And where do these electric charges come from? We have just said that these come from subatomic particles. And what we mean by subatomic particles are typically electrons and nucleus. This picture here shows you simplified structure of one atom. And atoms are made of nucleus at the center and electron clouds surrounding it. And we typically say that the size of an atom is as small as 2 times 10 to the power of minus 10 meter. And this is in fact not the size of the nucleus, but the size of the electron cloud. And each electron is in fact negatively charged, and the size of its charge is called Q, and it's actually, here you see that it's actually minus E, and minus E corresponds to minus 1.602 times 10 to the power of minus 19 coulomb. And we will soon see what this coulomb means. And then, in fact, the size of the nucleus is much, much smaller than the size of an atom or electron cloud, and it is as small as 5 times to the 10 to the power of minus 15 meter. So approximately it's smaller than the average size of atom by, say, 100,000 times. It's much, much smaller. And this nucleus consists of protons and neutrons. Both of them are subatomic particles, and among them each proton is now positively charged, and the size of its charge is exactly the same as the size of the electron, and only the difference is that now its sign is positive, so it's plus 1.602 times 10 to the power of minus 19 coulomb. And in the meantime, the neutrons do not have charges, so we say they are neutral, and then we say, and then their amount of charge is 0. And here we already used the symbol E for the electron. The size of charge is minus E, and the size of charge for proton was plus E, and this E is called the elementary charge. As you can guess, the symbol E actually comes from this elementary charge. And the reason why it's called the elementary charge is because it's the basic unit of the size of charges.